Good morning, everyone.
Action.
Yeah, that's next part of the movie. Again, the same boring actor. No beautiful girls on stage or something like that. I'm sorry for that, yes. So, good morning, everyone. I just had an interesting discussion with one of you, talking about textures and questions on texture measurements. And we discussed it shortly, and I figured out that would be something which probably concerns many of you. And I would like to motivate you later on, so I continue now a little bit stubborn with my own lecturing, but later on we should take time if such questions come up, like how do I measure a texture and is the texture trustful and so on, then it would be actually better to not discuss it only with me here privately at the board, but let's discuss it for everyone, because your question was actually quite interesting, and the answer to it is, I think, relevant for many people. No? So maybe we'll pick it up later again, and if you have questions out of your own daily routines, where you wonder, am I doing it right? Why not presenting it to me, and I try to answer for everyone, no? If this comes up later. But for the moment, let me continue with the lectures I have given. And just to repeat the last slide, not to repeat, but to remind you of the last slide, that was actually more or less this one here, introducing what is the Euler space and showing you how to use Euler space to display orientations. Yeah, that means every point in Euler space corresponds to an orientation, and you remember, if you have then many points, if you have measured many crystals, then you get lots of points. And once again, the awareness, every point corresponds well to one well-defined orientation, but one well-defined orientation may correspond to several points in here. And probably you could use, and I can show you later on, the OIM software or my own software, the Stoker software, to explore where are these points. Yeah? So if you say, I take now one well-defined orientation, where are the 3 points which belong to this orientation? We could make this exercise later. Then you would see nicely that there is actually symmetry also in these. Is this not working any longer? Oh, yes, it is. There is, so to say, but it's switching off. I better take the batteries are running off here now. I take the other one, I think. Okay, this is better, yeah. So there is crystal symmetry inside of these pictures, although the pictures themselves don't show a symmetry. Yeah? There may be a point here corresponding to a point here. I honestly saying, I don't know now either. Every point has 2 other points joining it, and I don't know where they are. So I would have to use my software as well to find them out. But this OIM software, for example, is a beautiful tool to learn about that. I will show you later. And then you start getting aware, this maximum here corresponds to this maximum or something like that. It's the same thing. It's the same crystal. There's not 2 maxima in this distribution, or 3 maxima, but only 1, but it appears 3 times. Yeah. So that's these points which you should be aware of. Good. The features of Euler space I have mentioned now sufficiently. We are not going through that again. And I will also not, maybe very quickly, there is another way of displaying orientations, and when you're working with cubic or hexagonal materials, it's very beautiful, and that is called Rodriguez vectors. And actually, again, what you, like every time in texture, you have a sample coordinate system, you have a crystal coordinate system, and you want to express how to rotate the sample into the crystal. And you can do this with the 3 Euler angles, but you can also do it in the following way. You fix one axis somewhere in space, and you say, I rotate around 50 degrees around that axis, and I'm rotating this sample coordinate system into this crystal. And there is a unique calculation way to do that, and then you get an axis which has the length 1. So the length here is, first you have any kind of axis, Ex, Ey, Ez, and an angle, omega. And now you make the following trick. So this is still 4 coordinates, yeah? 3 axis coordinates plus an angle. But you know rotation is 3 coordinates is sufficient. So how can you make now a 3 coordinate file out of it? You say, I define a vector which contains omega and the directions in one thing. And how do you do that? Actually, you take first, you make this vector, you normalize it. That means you bring it to the length 1. Yeah, that's very simple to normalize a vector. So, and then you multiply this vector of length 1 with the tangent of the half omega angle. That means this vector has a length, and this length represents the rotation angle, and the direction represents the rotation axis. And in this way, you create a new space which has now only 3 coordinates, actually the 3 Rodriguez components, Rodriguez vector components. And you can then go and display this Rodriguez vector again in a 3-dimensional coordinate space. Yeah? You say the Rx, the Ry, and the Rz are defining, setting up a Cartesian space, and any kind of vector, any kind of Rodriguez vector is simply a vector in this space. And the interesting thing is now this becomes a unique description. Yeah? And it has a lot of interesting, why does it become a unique description? This is actually not so simple to say. The symmetry of this Rodriguez space is more simple than the symmetry of Euler space. And therefore, you can actually more easily find a single vector corresponding to a single orientation. So you have a one-to-one correspondence. One orientation corresponds to one vector, and one vector corresponds to one orientation. This is a big advantage of this Rodriguez space. And furthermore, you actually, as I show it here, if you just have a coordinate about the first vector, the Rz, then this corresponds to a rotation about this angle here, about this vector here. If you have a component only about x, it only contains a rotation about this direction. So it's actually quite easy to understand this space. Yeah? It's easier to read. And how do you actually select a unique orientation out of these multiples of orientations? You remember in cubic systems, we have 24 different possibilities to describe the same orientation. What you do is you calculate this pair here, consisting of a direction and an angle, and now you will get actually 24 different angles. You will find 24 different axes combined with 24 different angles. And there is now a definition or a convention that you say, let's take out of these 24, which are physically all identical but mathematically different, let's take that one which has the smallest angle. And that limits us to the smallest Rodriguez space, and that gives us a unique description. And it's actually quite simple for a computer to calculate that. That's why it is beautiful to use this Rodriguez space. And it looks then, so we have, and when you then plot, we had the definition there already. When you then plot this Rodriguez space, you find that it's not a simple cube. So it does not end at 90, 90, 90 degree, but depending on the crystal structure, depending on the crystal symmetry, it has, for example, these cut edges here. So in the direction 1, 1, 1, rotation 1, 1, 1, it cannot rotate more than 63 degree, then it will jump into the next orientation. Yeah? And that is actually here, that's why these corners are cut off, because as soon as the angle reaches 63 degree, tangents of 63 degree half, it will jump to the opposite corner. There will be a symmetric or equivalent orientation coming up, being smaller in angle. Yeah? And therefore this cube has a little bit funny shape, and when you then reduce the shape even to orthotropic sample symmetry, then you're not having this whole cube here, or it's not a cube with cut corners, then it reduces to this funny feature here. And that is then the smallest space in which you can define every orientation uniquely once. Yeah? So it looks a bit strange, but it's easy to handle. And the only disadvantage of this space is actually that you can't apply it to crystal structures which have no which have only dyadic, it's not defined, there it is, on crystal structures which have only dyadic rotations. That means only 180-degree rotations, because this tangents omega half will then become infinitive. Then the space will run to infinity. Yeah, if you have a rotation, 180 by 2 is 90, and tangents of 90 is infinity. So for these crystal structures, and that is monoclinic and triclinic, this Rodriguez space is not defined. For all others, you can use it very nicely. Yeah? And it's a beautiful way of representing orientations. Oh yeah, here I even explain what I mentioned here. You have the limitations of these surfaces here. That's tangents 45 degree, a rotation about 0.01. Okay, you see it there. And that is the largest rotation possible in a cubic system. It's 62.8 degree. I don't prove that it is like that, but you have to accept it for the moment. And then, this is also a very interesting finding, or a very interesting feature of the Rodriguez space. You remember, Euler space is not homogeneously filled. If you're close to capital phi equals 0, then the orientations are farther away than when you are far away from it. Yeah? And this is almost not the case for the Rodriguez space. If you place orientations, each one 5 degrees spaced, they have in Rodriguez space almost exactly the same distance from each other. And that makes it actually quite nice. I think I show it here. Yes, exactly. So this is a cut through this space, through this surface here, and I plot lines with 5 degree difference in orientation. And you see these lines almost have everywhere the same distance. They get a little bit wider here at the end, but it's almost invisible. Yeah? So actually these orientations are all equidistant spaced, and you see it's almost an equidistant filling of this Rodriguez space. So I must admit I don't use the Rodriguez space very often, because traditionally everyone looks into Euler space, and if you then compare textures from literature with your textures which you want to maybe explore, then it's often inconvenient because one is in Euler space and one is in Rodriguez space and you don't see. But in principle it would be good to go, and everyone uses Rodriguez space. Yeah? But okay, that's, I mentioned what is the problem. Another point, I should almost make this exercise with you. If you have fibers, that means you have crystals and they all rotate just about one axis, wherever this axis is. Then in Euler space, they make funny curves. And I will show you this in a moment. But in Rodriguez space, they're all straight lines. And then you can see more easily, this is a fiber, this is a rotation just of crystals around one axis. And let me give this exercise shortly with my funny computer program. So we start that here again. Which one do we take? This one, for example. Okay, good. Simulation data display. So we're looking for the Euler space. And can I display as well? Oh no, I cannot display the Rodriguez space at the same time. But okay, that doesn't matter. Let's rotate the space such that we see a bit and show it completely. And now I will make a little fiber. That means I will take a crystal, and what should we do? What kind of, let's start with one somehow selected crystal. So I start with this crystal, set. So, and now I make a regular rotation, let's say in 5 degree distances, around that axis, set. And another 5 degree, set. And another 5 degree, set. And another 5. And I make some 10 crystals or something like that. So each time I rotate 5 degree. And you see already that this makes a funny shape, yeah? Okay, so I just have rotated regularly always around the same axis. And you see now that it makes that the Euler space gets some funny curves. Okay, good. And now let's look in the same thing in Rodriguez space. Rodriguez, okay. So that's the Rodriguez space. And you see it's just a straight line. Yeah, okay, the straight line starts coming out. It started here, and then it jumps when it touches the surface. It jumps in from the other side again. Yeah, and it's just a straight line, and very nicely to see. Now you have learned around the stereographic projection already. So let me show you also the stereographic projection of this funny exercise. Let's say the what I plot here is just the stereographic projection showing just the 0, 0, 1 plane poles of all the crystals. And you see that was my fiber. I started rotating here, and then it rotates actually the three poles. There's 3 or 1 poles in the cubic system. Yeah, they all rotate here around. We can make it a little longer. So I continue with some 5-degree steps, up, and some other 5-degree steps, set. And so you see how the spaces are slowly filling with numbers. Now if I would start making a rotation about a different axis, so let's say starting around y, and we set, and another y 5-degree, and another y 5-degree, and another one up, okay, up, and so on. So you see in the pole figures it makes a different, also not a straight line, of course not, because it's a stereographic projection. It's a spherical projection on a flat. It cannot be straight lines, yeah. But in Rodriguez space, it is really a beautiful, yeah, I need to move it, otherwise you can't see it properly. No? It's a beautiful, actually straight line, yeah. And let's go back to the Euler space here. Euler space, this is quite terrible, yeah. No one sees anything any longer. And if you have then overlapping fibers, or they have a certain width, then it becomes quite tricky to see that. Let me show again the most basic, this one here. And you see now we have even not only 3 fibers, 3 lines corresponding to this, but we see even a number of points. Yeah? While in Rodriguez space, once again, Rodriguez in principle, you just have one straight line. It's actually easy. Rodriguez space is something beautiful. Yeah? It's nice to handle it. And the OIM software offers you the same possibilities to handle Rodriguez space as the Euler space. Just traditionally, historically, Euler space is more used, and therefore that's probably the reason why everyone is stuck to that. No? And yeah, and this one was the O1 pole figure, but now I make a nice exercise for you, showing you the 1, 2, 3 pole figure, yeah? And this is not fun, but it's just to make you confuse. 1, 2, 3, okay. Here we go. This is looking like that. Why that? Why is it so full? Because you know 1, 2, 3, the plane 1, 2, 3 has 24 variants in the crystal. And that means for every crystal we have 24 points in here. And then you rotate the crystal, you will rotate 24 points, and you overlap them all. Of course you don't see anything any longer. No? And it would be very unlikely that you ever look into a pole figure of 1, 2, 3 type of our crystals. But maybe there is some particular physical property which is particularly active on 1, 2, 3 planes. I don't think that there is one. No? But in this case it would be perhaps helpful to look into 1, 2, 3, because then you would see some clustering there. Yeah? Most probably in cubic systems, in cubic systems we know that, for example, the densest packed planes are either 1, 1, 1 or 1, 1, 0. And so therefore it is reasonable to look into these ones, 1, 1, 1 and 1, 1, 0, or into the densest packed directions, which is 1, 1, 0 and 1, 1, 1. So it makes often sense to look into these. But for example, I told you the BCC material slips on 1, 2, 3 planes. Yeah? So it may be, if there's really material which has a slip on 1, 2, 3 and not on 1, 1, 0, then you may see actually some features in a 1, 2, 3 pole figure. Very unlikely, because the 1, 2, 3 slip in BCC is little, but there is still a little possibility that this makes sense. Yeah? Okay. I hope that is a little interesting, speaking about Rodriguez space and about the use of orientations. And yes, good. So we had that all. We go over that. And once again, the only disadvantage I really see for the Rodriguez space is that it's not valid for all structures. Yeah. All right. And the last one, this is a bit for curiosity. Many software works based on quaternions. Software, from point of view of software, quaternions are very helpful because they make a very small error during the calculations. And how are they defined? It's a 4D space instead of a 3D space. And this 4D space has the advantage that the algebra becomes easy. Algebra of Euler angles is terrible. Yeah? Actually, you don't want to do that. No? And even in Rodriguez space, because you have this tangent in there, it's not so simple to handle. But the quaternions, which come originally out of quantum mechanics in order to describe the behavior of quantum mechanical systems, have been defined such that algebra is simple. So you also see here a sinus and a cosinus, but there is some rules which allow to add and multiply and divide quaternions. So for example, a misorientation is just the difference between two quaternions. Yeah? You just take a 4D vector and the second 4D vector, you calculate the misorientation just by subtracting vectors from each other. Beautiful. That cannot be quicker done than that. No? And the rules are written here. I don't want to go into details, but for manipulating in the software, in computer, quaternions are very powerful. Of course, you cannot display them easily because it's 4D and not 3D. You always have to go back to some 3D or some 2D presentation. But for calculation inside, I write it here, pile up of numerical errors can be avoided quite significantly. And for example, very beautiful to calculate average orientations. Yeah? This is something you often do. You have a grain and you want to know, and it has many different points inside, and you want to know what is the average orientation of that grain. You may see in this corner it's rotated a bit like that, in that corner a bit like that. What's the average? With quaternions, you just add like an algebraic average. You just add these quaternions together, divide by the total number, and you have your quaternion average. Yeah? Approximately, it's like that. No? Good, that's quaternions. Oh yeah, that's written how to calculate the average even. Yeah. Mm-hmm. So it's actually quite simple to do. So, and now with a bit more time, we're coming to the metallurgical description. And because this is very frequently used, also in OIM program, in the Oxford program, in my own program as well, it's quite a traditional use. And if you have it, it's also it's intuitively understandable. And what is it actually? Let's forget about the text. You have a crystal in a sample. So here's my sample, and inside there may be a crystal. So this is not a square crystal, this is just the lattice of the crystal. Around this there may be the crystal. And now I want to describe how the orientation of this crystal stands with respect to this coordinate system. So what I will do is, I set a coordinate system, of course, and still I'm a traditional metallurgist, still I call it rolling direction, although in a modern material you just should call it X. Yeah? There is maybe, on a solar cell you probably don't have a rolling direction, yeah? But still you have a texture. Yeah? And on many materials which have been extruded or deposited in some way or whatever, or sheared, there is no rolling direction, but it's just the principal direction X. And there is a normal direction Z, and there is a resulting direction Y. And always think, also important as a hint for everyone, when you deal with coordinate systems, look on your right hand. If you want to understand coordinate systems, X, Y, Z. No? If you do it with the left hand, by chance you're a left-hand writer and you think, oh, I look for X, Y, Z, then you get everything wrong. Yeah, not really wrong, but then you should remember that then all rotations must be inverted, no? Into minus. So look on your right hand, then you have your correct setup of a coordinate system. As long as you have not dealt with that, it's not a problem. But when you're dealing with textures and you want to do a texture analysis, you get quickly into trouble when you're not setting up coordinate systems correctly. So you say X for the sump. Oh, this is now a bit difficult. Right hand, X, Z, xz, no? So, and then y points out of the picture here. That's important. It does not point in. I know so many of my students come with trouble. Yeah. Why does this not fit? Why am I rotating the wrong way? And particularly when you do then correlation with grain boundaries or with dislocations in a real image, suddenly the things do not match. Yeah. So you have a picture and you see a grain boundary of a twin. So you know this should be a 1, 1, 1. But in your pole figure, the 1, 1, 1 looks like that. So why is so the 1, 1, 1 is indicated to be perpendicular to that? No? Why is that? What have I done wrong? And then it's often that you have mistaken right and left hand. Yeah, and then the picture and your pole figure does not fit any longer together. Yeah, and that's trouble. Of course, once again, most of the software takes care for it. But as soon as you start manipulating a little bit by yourself, no, then you must be aware that coordinate systems are something to tackle with care and with attention. I repeated it too often already, sorry. Good. So we have fixed our coordinate system, and now we want to fix our crystal. And we say, okay, which direction of my crystal, and I call this direction UVW, is parallel to the principal direction of my sample, and which second direction of my crystal, or I call it which plane, is parallel to the surface plane of my sample. And I call this UVW for a direction in X, and HKL for a plane perpendicular to Z. And these two numbers I mention, these two numbers, these 6 numbers I mention, and I get a unique description of a crystal. Yeah? And when I tell you, HKL is 1, 1, 1, then every one of you probably can imagine, where was my piece of soap? Here. Yeah. Everyone can imagine that I need a second thing. I need a sample. Oh yeah, here's the singing lady. So I have a sample and I say 1, 1, 1 is HKL, then you know immediately that the crystal stands like that with the corner up. Yeah? That is the orientation of it. No? And when I say it's an 001, HKL is 001, then all one knows it must stand like that. We don't know the rotation here around, but we know this direction must be it. No? And then if we know UVW is also 001, then we know, then it must stand like that. Here's a UVW, here's an 001, and here's an 001. That must be the orientation. No? And when this is 1, 1, 1, and the other one here is 1, 1, 0, 1, 1, 0 does not fit. 1, 1, 0 does fit, yeah. So then you know it's standing like that, and one corner is standing like that. So I can actually, for you, I can make that exercise even in front of you without preparing myself too much. By reading out what is HKL and UVW, I can show you the orientation. If you tell me, show me Euler angle 20, 30, 40, I have no clue how to show it. No? I don't know. But HKL, UVW is actually quite simple to imagine. That's why it is interesting to care for that. And you will see, it's not only interesting to care, it's also opening a new and important world for us. And this is the world of pole figures. I have spoken about pole figures now already, but we need to repeat that again. So I mentioned already a lot of pole figures, stereographic projections, and I plot in the stereographic projections the crystal coordinates. No? And this is all called a normal pole figure. So I plot the crystal coordinate system inside of a fixed sample coordinate system. Let me make that again. Pradeep, sorry that I'm still insisting on all this basic stuff, yeah. But I think then all the other things become easier. I know you want me to just expand to examples and so on, but okay, good. So, and you may, yeah, good. Of course, it could be that you know it all. Of course, then. Oh, this is not plotting. This one here. Again, our stereographic projection. Whoop. So, and I fix the stereographic projection such that I say, oh, good that I have at least these two examples here. the stereographic projection will represent my fixed sample coordinate system. Yeah? So I will say here in the middle, this is the direction ND, which perpendicular on here, and this one here is the so we call it also Z, and this one will be X. Whatever this X means, it could be rolling direction, extrusion direction, shear direction, whatever you fix it. Good. And now I take that and it's fixed, and of course then here is a Y. And now I plot my crystal inside. Now I say, for example, I plot all the 001 planes, and I will have 1, 2, 3 points for one crystal. So that's a normal pole figure. I fix my sample and I plot the crystal inside. And this is a little example how to do that or how to read it, what I explained already. So for example, I plot the 100 poles, and here I plot as a second example the 111 poles. Yeah? So the corners, the corner directions. So let's take this most simple crystal. So the square here around indicates the sample, which is positioned X and Y and Z, and the little square inside represents the crystal, as plotted with my little computer program. So for this one here, we know the 001 should be pointing out, and it should also point to the left and to the right and to the top and to the bottom. So we should have points, 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 and points. And indeed, come on, show me. These are the points I will get. Usually I told you there should be 3 symmetrically equivalent points for the 001 planes, yeah? But we see 1, 2, 3, 4, 5. The reason for that is only that this pole and this pole is the same. It's just the front and the back side of the same plane, and this one as well. So it's actually only 3. And if I would rotate a little bit away from that position, this one would come in and this one would come out. We would have only 3. So the orientation here I call 001, 100 in form of the metallurgical description. So there's a 001 plane here and a 110 direction here, 100 direction here. So that is the metallurgical description, and that is the pole figure with it. And the same, if I plot now the 111 planes, that means the directions of these corners here, it makes these 4 spots here. Good, now the next example is a crystal which stands just like that, tilted 45 degrees. And of course then now this direction here, coming out of the plane is an 011 plane, and this direction is still a 100 plane. So we can plot that in here. These blue dots here, plotting the 100 planes, the 100 planes, this plane here and this plane here, and the front plane and the back plane, they are here, 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 here. And if we plot the 111 corners, so here's one corner, here's one corner, here's one corner, here's one corner. I plot them in here. You get these ones here, and I should have actually plotted this one, of course, repeats here and here. I should have plotted that as well. So that is this orientation. Now let's take a more general one. In this case, we are looking again on a 111 plane. This one here is a 111 plane. We're looking exactly on the corner of the cube. And this one here is something more complicated, a 211 direction. So 111, this, you see where the 001 planes, they are here, here, and here. They must come out here, here, and here somewhere. And indeed, there they are. No? And the 111 planes, of course, one is pointing directly out. It must be here in the center of the pole figure. Yeah? And the others are at a little bit more different positions. I just plot them. Come on. There they are. No? So this is 4 poles to describe all the 4 corners. 3 poles to describe the 3 surfaces. And if I would plot 110, you would see 6 poles there. And then last example, it's 4 different and simple examples. 001 again, so we're having an 001 plane and a 110 direction. And if we plot that in here, now it starts getting boring. The green dots, and here, these dots here. Okay, so far that's probably clear. And you have to read it like that you usually have, in a 111 pole, you have 4 equivalent planes. Here you have 3. In a 110 you have 6. In a 123 you have 24. And if you have something in between, you may have also, do you have also situations where you have 12? I'm not quite sure. Yeah, probably 120 or something like that. When you have 10, then you have 12 equivalent positions. Okay, but this is normal pole figures. And now we make the step to inverse pole figures. And you will see this is super important when you handle with EBSD, because often you see inverse pole figure maps. And I'm not quite sure whether every one of you knows what that is, the inverse pole figure map. But first we need to plot inverse pole figures. So inverse pole figures means now, this time I'm keeping the crystal coordinate system constant, and I'm plotting the position of the sample coordinate system inside. So that means this time it's a bit more difficult to imagine it, and therefore or to plot it myself here on the board. That's why I rely on the drawing here. So this is my crystal coordinate system of a cube standing like that, of a cubic crystal standing like that. So here's the 001 plane, here's another 100 plane, here's another 010 plane. It stands just as a standard setup, and we keep it like that. It will not move. And now we have, of course, okay, let's go again to our example. You remember, I had a crystal somewhere standing in there, and so somewhere standing in here, and I said with the metallurgical description we describe which direction of the sample, for which, I need to select my words, in which crystal direction points the rolling direction, and in which crystal direction points the normal direction of my sample. So I know that, and I can go and plot that now in. So now I should not draw on that one here. So for example, I find my sorry, I'm running too much back and forth. Let's assume my crystal orientation was found to be 100, so with round brackets 001. Okay, that was my HKL UVW. So where would that be in my crystal, in my coordinate system here? So let me show this. Pointer, this one here. 100 for HKL would be here. And what did I say, 001? So this one would be Z, right? And 001 would be here. So, and I could make another one. So let's give it different symbols. This would be the X direction here. And maybe for X I make an X really. And for Z I make a circle. Okay. Now let's imagine just another crystal orientation. And now you will see already one of the tricks. I will make another orientation which is 010, 001 as well. Okay, let's do it like that. Yeah. So let's plot that one. 01001. This would be here and here. Yeah. So I could plot these two poles in there for the crystal coordinate system, for the sample coordinate system. Or let's make a third example. By the way, you must always make sure that these two vectors are perpendicular to each other. Yeah? That's why I looked whether I'm getting the right angle. So 1, 1, 1, 1, 1, 1. And then we take 0, 1, minus 1, for example. Okay? That is a reasonable orientation because these two vectors are perpendicular to each other. Let me do it. 1, 1, 1, we said. 1, 1, 1. Yes. I don't see it here. It is 1, 1, 1, of course. It must be here. And the other one I said 0, 1, minus 1. Yep. I hope it's on the screen. 0, 1, minus 0, minus 1, 1. It's on the opposite side. Yeah, but it could be this one. It's just on, unfortunately I took it from the back side, but we can also take this one, 0 minus 1, 1. This one here. This one here we delete. Okay, so we have an orientation. Let me connect these two, then you can see it easily. We have this connection here, or we had this connection, or we had this connection here. So these were our few orientations. And you see, however, it becomes a little bit bad to see. And one more thing, I told you that the crystal direction 100 and 010 are symmetrically identical. Yeah. So why do I select now this point and this point? Why not always this point, or always this point also? So, and also the 011s are symmetrical, or 111, and I could have selected here 1 minus 11. It was my free choice to say, okay, I want 1 minus 1, 1, and then then I have to change, of course, 011. This would be symmetrically the same orientation, physically the same orientation than this one. I just have permutated the mathematical description. Yeah. So although it's physically the same, it will appear in this pole figure here at a different place. So that's a little tricky. Yeah. It makes it actually quite complicated. Now let me clean up shortly my drawings here again. No, I just leave it here and verwerfen and start again. So, and now comes the trick. I think this was a reasonable good introduction which I made. So we are plotting our sample in there, but what we do is we limit ourselves to an area where we actually get a unique description of these, where these crystal symmetry operations don't play a role any longer. And that means we limit ourselves to this little triangle where there is only 101 position, and only 110 position, and only 111 position. This is the so-called the asymmetric crystallographic unit, yeah, or the asymmetric orientation triangle, yeah, or the unit orientation triangle. There is a number of words. Oh, standard orientation triangle. This is the word. So in order to have this problem that two symmetrically equivalent things appear at different places, to solve that, we are all plotting it into this standard orientation triangle. And so let me show, and now, next step, difficult. I showed you that for every orientation we need two indices. We need the UVW and the HKL. And if I plot that both into the same triangle, I don't know any longer which one was which. So I take two triangles, one where I plot UVW and one where I plot HKL. It's the same triangles, but they show, one shows the X direction and one shows the Y direction of my crystal. Yeah, that's I'm writing here as well, X, so UVW is corresponding to X, and HKL corresponds to Z. Good. And now let's make the same exercise again. We have a crystal like that with the orientation 001, 100, metallurgical orientation. And we can now read immediately where that is in these stereographic projections. 001 for HKL, that means it must be appearing here. And 100 for UVW, that means it must appear as well here. Yeah? 100 is the same as 001, so that's why. So let's plot it, and indeed, I was right. Yeah. Now, let's plot another one. This one, you remember. 011, 100 is the orientation. 011 for HKL will appear here. 100 will appear here. Let's plot it. There it is. Next one, this is a bit more complicated. 111 is appearing for HKL. That means we'll get a point here. And 211 is for the direction UVW that appears somewhere here between 111 and 001. So let's plot it. There they are, these 2 points. Yeah? And finally, the last one here, 001, 110, 001 for HKL. That means it will appear here in this corner. And 110 for UVW, it will appear in that corner. And I plot it here. Good. And of course now I have not taken any orientation which fills the center here, but just because the numbers are not so convenient then. No? I could plot a 1, 2, 3. A 1, 2, 3 would somewhere be in here. And then of course, if I, where did I leave my pencil? Over there. if I use a 1, 2, 3 for HKL, for example, now I have to find a UVW which is perpendicular to it. It could be, for example, 6 what?
6345.
Yeah, exactly. 6340, for example. Huh? This is, if I do it like that. Now then I have 1 times 6 plus 2 times 3 plus 0. Yeah, but you are right as well. Just to make it a simple coordinate system. No? But it's sufficiently complicated. Now we would find some 2 points in there. Honestly saying, I am unable now to plot where is 6, 3, 0 and 1, 2, 3, but it's somewhere inside of these poles. Yeah. Okay, good. All right, good. So, and now comes a beautiful step forward. We can now say, okay, we can plot these inverse pole figures, and you will see pole orientation software does this. But we can now do another thing. We can assign the position in this triangle with a color. And we do this with a nice rainbow selection, which is here. That means whenever a pole is close to 001, we'll give it a color close to red. When it's close to 110, we'll give it a color close to green. And when it's 111, it's close to blue, and all the mixtures in between. And that means just by reading out the colors here, we are able to say where was this crystal. And that means this crystal here, for example, would appear, if we would plot it now in the map, we would give it a red color. Yeah? Red for both 001 is red and 100 is also red, and so on. So, and that's actually the inverse pole figure map, which we then see very frequently when we use EBSD. We are actually taking these colors out of the inverse pole figure, out of this, why is it not coming? Out of this overlay of color triangle. And we are plotting for every crystal, actually for every point, we are plotting the color it has in this inverse pole figure map. And we plot that for UVW, that is one set of colors, and we plot it for, oops, there it is, for HKL, that is the second set of colors. So with these two sets of colors, we get a unique description of orientations, almost unique, almost unique. There is a trick, actually. Oh, you are aware of it, yeah? This is an ugly trick, actually, and I will shortly talk about it. But let me first talk about this one here. So now we see, okay, let me make an exercise, UVW, an exercise for myself first, yeah? I try to find a grain which is easily colored. For example, this here and this here. This is sufficiently easy. So it's the same grain. It is in UVW, it's 110, and in HKL, it is 111. So this seems to be UVW 110 or 011, and this one, oh, this is it's by chance exactly the orientation I wrote down here as last. No? So this grain here, indeed, has the orientation 111, 110. And we could look, let me show you this shortly. The cameraman is very busy with me running back and forth, yeah? No, is it all right? No, it's okay. You're not following with the camera. I'm running back and forth, I'm sorry for that. All right, let me show you shortly with TOCA. Simulation, FCC. The orientation here, the other one. 1 second. So I plot the orientation. What did I say? 111, 110, 110, yeah. 111 for HKL, and 1 minus 1 0 for UVW. And let's click that away here. So that would be, here it is, that is the orientation of this 111, 110. No? I could probably plot it also by myself, but you see this reading out of the inverse pole figure is relatively straightforward. We can relatively easily understand this crystal, which I have plotted there in green and blue, has this orientation here. Good. Here we were. And I have made this exercise already before with my in my animations. So we see here 2 red grains and 2 yellow grains. Good. You have understood how to read that. It's clear. And what I want to show now is I plotted now for these yellow grains the orientations here, and for these yellow and red grains the orientations, and I calculate the misorientation, and it's 44.8 degrees. Huh? And you say, similar color, shouldn't that indicate similar orientation? Yeah? And this is a trouble, because similar color means only symmetric directions. Yeah? But one here is, I don't know which orientation it is, but this one here is probably something like a 1-3-0 direction, and this is probably a 3-1-0 direction. So, and I combine this both with an 0-0-1 direction here. So in this case, we are getting symmetric directions, but not symmetric or not identical orientations. We are getting identical directions for this one and for this one, but not, and for this one and for this one, but the combination still leads to different orientations. So same color, but nevertheless not the same grain orientation. Yeah? Symmetrically equivalent, but not identical. Another example, green and red-blue. Okay, this is clear. That must be different. Yeah, let's plot that here. And it's indeed green for UVW means that here for the horizontal orientation there must be a 1-1-0 direction. And we see that actually this is the corner here is a 1-1-0, and here is another corner which is 1-1-0. So both have 1-1-0. And it is red and blue. That means once we look on the 0-0-1 direction for the red one, and once we look on the 1-1-1 direction for the blue one. So we look on the corner or on the face. So that's quite unique. And then a third example. Okay, where is the third example? Right here. This is blue-pink and red-orange. So you would say quite different. But if we look on that, it's almost the same orientation. Yeah. So the colors can also cheat a little bit. No? The colors tell you it's quite different, but the misorientation is actually only 12 degrees. So this is a couple of, this is an easy case. This is a case you have to think a second time, and this is also a case you have to think a second time when you read that. But the basic principles, I hope, are clear. Now, one of the serious problems is really, okay, if I have the same color, but I do not have the same orientation, what is that problem? And this leads me to just a short side remark. You don't have to digest that fully, but let me just make you aware of it. The problem is that when we do this creation of this color triangle, we do not consider that there is actually a mirror plane in here, which is not existing in the correct data set. Yeah? So in principle, in the original rotation data symmetry, in the original symmetry, in principle, this triangle here, which I have selected, when I really look on orientations and not only on directions, this triangle must be double as big in order to cover every symmetrically different orientation. Let's skip that one for the moment. And that is actually this question about the standard orientation triangle. There is one version which uses so-called improper rotations, where you always invert, where you always have also a mirror plane inside. But in rotational setups, you must not have the mirror plane. You must have only rotations. And there is a second one which consists only of proper rotations, and this allows us to do the proper orientation display. If you want, you can later read through that. I don't want to spend more time, but I just want to show you the graphics of that. This is the stereographic orientation triangle which we have used, and we assumed that there is in this rotational setup a mirror plane here. So if there is an orientation here, it will be mirror 1, 2, 3. It will be mirrored into 2, 1, 3. That will be the same. But when you consider rotations of crystals, there cannot be a mirror plane. There can be only rotations. And that means this one can no longer be transferred into this position there. And therefore, we need to color a larger triangle to have all proper rotations considered. And then our orientation triangle is no longer small, but it's this funny construction here, which we have to color from red all the way to green and blue. The coloring is then not so simple as it is in this case here. And nevertheless, you can do this with the software, with the OIM software. Exactly. So that's good to have here. We have here an orientation 1, 2, 3, 5, 1, 1, and here an orientation 2, 1, 3, 1, 5, 1. So both directions are identical. 2, 1, 3 is symmetrically equivalent to 2. 1, 2, 3 is symmetrically equivalent to 2, 1, 3, and 5, 1, 1 is symmetrically equivalent to 1, 5, 1. But the orientation, this one and this orientation, is not identical. They have a misorientation. Yeah. So directions is good, but tensorial orientations is not good. And therefore, if you want to just display directions, this one is sufficient. If you want to really get the full correct orientation, you must go to the version with the proper rotations. And then your map, which I showed you before, looks like that. And it looked before it looked like that, and now it looks like that. And now, with this color coding, you can actually get a unique orientation. You can read out when this is blue and this is green, and you look up, blue is here somewhere now and green is here somewhere. You will get a unique description of your orientation. There's no longer the fact that if two grains have the same color, that they don't have the same orientation. This cannot happen in this color coding. I know this is a relatively complicated concept for beginners, but it can be quite confusing also for people who are just starting to deal with it. No? Why do I see similar colors, but the orientations are not similar? Okay, this is just a teaser for you, to make you aware that there is a difference between proper and improper rotations. Okay, and this one, this is a last thing about that, and then I will stop with all these colors and rotations. So this was the standard orientation triangle for improper rotations for cubic systems. But for other crystal systems, these look different. The symmetrically equivalent unit is different. For example, for the hexagonal system, it is this one here. So you will color it here red, here green, here blue. For the, there it is even, yeah. For the tetragonal system, it's just a 45-degree slice. Yeah. For the trigonal system, it's a 60-degree slice, pi slice. And there is one. For the orthorhombic, it's this 90-degree area which covers the whole unique direction space. For monoclinic, it is the half sphere. And finally, for triclinic, the whole sphere is the only unique direction space. Every orientation is symmetrically different from the other. There is no symmetry inside. No? And that means when you work with triclinic materials, mainly probably with rocks and minerals, then you will plot, you will need the whole stereographic projection to display a position. There is no symmetry inside. Yeah? Okay. Good. Oh yeah, this is of course, later on you may read through this. I have spoken so long about it already, now it's enough. And with this, here we make a little break, at least in our brain. I heard I should make a break at 11:45. No? So I will still treat you 45 minutes longer, half an hour longer, with texture analysis. And then we are also done with that. Yes, it's a good point also to ask questions. Yes?
When we say disorientation,
yes.
Is that just the distance in Euler space between 2 points?
You mean the Cartesian distance?
Yes.
No. In Rodriguez space, it is about the Cartesian distance, also not perfectly, but almost. But in Euler space, as the Euler space is compressed, yeah, the Cartesian distance is different from the orientation distance. You remember, I plotted points of equal misorientation, and they were further away, close to capital phi equals 0, and closer together, away from that. And that means if you measure just the Cartesian distance, you say it's 2 pixel distance. It's not, that depends on where you are in space, whether this is 2 degree or 4 degree. Yeah? So the Euler space is in this regard not so convenient. Yeah. Then you need the software which calculates how big is the misorientation. Misorientations I will speak about in a little later. But it's a very valid question. In Rodriguez space, you can almost go with a ruler and measure, okay, if it's 2 centimeter up distance in my drawn space, then it's everywhere 20 degree misorientation. Yeah? But in Euler space, it cannot be done like that. And the best is, also for Rodriguez space, not fully valid, the best is you calculate the misorientation. That's the best. Yes?
You said quaternions for calculation Faraday orientation of vectors.
Mm-hmm.
So like in Euler space, like 0, 0, 0 and 0, 90, 90 are equivalent. That's like cube thing.
Mm-hmm. Mm-hmm.
So if I'm trying to add up to orientations, so it's easy to add in quaternions compared to Euler. Is it something like that?
You still, also when you work with quaternions is just a fundamental mathematical set of rules. It doesn't know anything about symmetries. So you have to bring in the symmetry yourself first. And that is indeed important. And so the set of quaternions is very simple to write. Yeah? You need just a few lines of code, you have your quaternions. But then you need more lines of code to consider that there is actually the quaternion for 001, 110 is different from the quaternion for 100, 011. Yeah? And this symmetry needs, although quaternions are easy, you still have to deal with the symmetry yourself. You have to write the code. Of course, if you use MTeX or any kind of software, this is already incorporated. But whenever you use OIM or whatever software, internally, that's all these calculations of symmetry are always going on. It's quite amazing. And once you have written this code yourself, you wonder why can they make it so quick? Yeah, that they treat millions of data points in a minute, although for every data point you go to 500 different calculations to find out is it the right orientation or not. You will see that later on. Yeah? A misorientation between 2 points has 500, in a cubic system, 500 something, yeah, symmetrically, how many?
24.
Yeah, 24 times 24, exactly. Symmetrically equivalent representations. And in the software, always, all these calculations are done. Yeah, for every point you calculate. And you wonder how can they make it so quick? Because they use quaternions, but still they need to do all these symmetry operations. Yeah? So that's why I insisted so much on symmetries. This is in this crystal, when you deal with crystals, it's not only rotation. It's a rotation plus a consideration of the limits of symmetry. No? All right. Water. Can I go on, or should I answer some other questions? Not. Okay, then let's try texture analysis. We'll keep it short. Why texture analysis first? I think probably most of you know it, and I have a beautiful example, which is a famous example from texture research. It's the Goss texture, and actually, I hope I have a drawing. Yes, I have. When you make electrical transformers, you know you have a steel core or an iron core, a soft magnetic core, and you have a winding, an electric winding on one side and another coil on the other side. And by induction from one into the other, so you induce an electric field, a magnetic field by induction, and this magnetic field induces an electric flux in the next winding here in the next coil. So important is, and you imagine every electricity, everything what we are using goes through transformers, and not only through one, but through many often. So if you want to have small losses, you must optimize transformers. It's virtually all electric energy we ever use, except from batteries, is going through transformers. So it's a very important issue to make these transformers as efficient as possible in order to reduce energy losses. Transformers get warm, and that's the main losses then. And big transformers are as big as this area here. Yeah? 100 tons of steel just for a transformer, 100 ton of steel for a big super power transformer. So it's important to optimize that. And for this, in order to optimize this, we need to know one thing: the magnetic flux is not going through a material, it's not going without resistance. But depending on what is the crystal orientation, you have a high or a low resistance, you have a hard magnetic direction or you have a soft magnetic direction. And this shows, this is plotted here. Here you have the magnetic field, and here you see the saturation, the magnetic saturation. So for a given field, you can read, have I already fully saturated my field, my magnet, or is it not yet fully saturated? And you see for the 100 direction, it's most easy to saturate it. So the magnetic resistance is most easy. So we would like to have a crystal direction in 100 to have a perfect transformer. It very quickly, we need just a small magnetic field, we are already fully saturated. No? While for the 111 direction, it's really, you need a very high magnetic field to reach full magnetization. So resistance of 111 is highest and 110 is softest, is lowest. So the best would be we could build a transformer like it is here, which consists of crystals standing like that, 100, So then always the magnetic flux would follow just the softest magnetic direction. This would be perfect. But unfortunately, technologically, we cannot make a 100-ton steel block which is out of a single crystal of 10001. This is impossible in steels, particularly because you have a phase transformation from high to low temperature. So you could not also using a bridgement technique, for example, to draw these crystals or so. But Mr. Goss, some 80 years ago, found that there is a fantastic way to create another form of orientation in a large technological amount, in large technological amount, yes, right. And that is the Goss texture, named according to him. And this texture is actually having 110, 001 as the direction. So one direction is 110, but the second one is 001. And you see it here, 110 is okay, it's not so super, but 100 is very good, so we have a good compromise. And there is a technological way to make a 100-kilometer long steel sheet, all consisting out of this Goss grains. For me, it's still a miracle, and I think to everyone who has ever studied that, I'm still studying it since 15 years. It's still, for everyone who has ever dealt with it, it's a miracle how this texture can develop. And it develops actually, I hope I have it here as a picture. Yes, I do have. So that is once again, that is the typical Goss texture. So you have a 110 normal direction and an 001 rolling direction. Yeah, that is called Goss texture. And it forms during secondary recrystallization, also called abnormal grain growth. And that looks like that. Now, luckily, you are all already able to read this plot of the Euler space. Yeah? So here you see the different sections of the Euler space from 0 to 90 degree. And I didn't plot individual points for all the orientations, but I plot how many points are standing at which place, the density distribution. And you see for primary recrystallized material, this ODF, orientation distribution function, is relatively soft. Unfortunately, I can't read the numbers here, but it's in the order of 4 maximum intensity. We'll in a moment learn what that means. And now we let the material, we heat the material up slowly to 1200 degree. And during this heating up, the material suddenly starts growing. A few grains start growing enormously and eating up all the other grains. And at the end, you will find all these grains, all the grains which have grown, had all the Goss orientation as a big mystery. It's still not understood. I think I have a theory why it is, and we're currently proving it, and then we will write up a big paper solving a 100-year-old problem. But anyway, after this recrystallization, secondary recrystallization has happened, all the orientations have changed. There's nothing left of that, and it's only the Goss orientation left over, this 110-001. Yeah? And that's, as I said, this is almost a single crystal. It's not perfectly a single crystal. It's one grain here, one grain here. The grains are finally centimeter big. Yeah? And one grain, one Gauss grain, consumes during its growth 1 million of other grains. So it's only 1 out of 1 million, or in some special high quality steels, it's even 1 out of 10 million grains which decides to grow. And miraculously, this is all Gauss oriented. Yeah? Why is that? That's quite a miracle, and it's also quite a nice display why it's important to care for textures. You want to make sure that these textures are right in order to make these textures perfect. No? And so you need to know what is texture. So the crystallographic texture, as a definition, is the volume density distribution of crystal orientations. So you say, how much volume percent of my material has a particular orientation? And I can say 20% have Gauss texture, 40% have cube texture, 30% have S texture, and whatever. And this distribution is called the texture. And you can also say there is no texture, or the texture is random. That means there is no preferred orientation which has higher volume fraction than a random distribution of all grains. Yeah? So we can say a sharp texture has a high density of one given orientation, a weak texture has a low density. And here's my no texture or random distribution. And this is not animated. Okay, usually I go step by step through the text. But okay, that's all right. The texture is created by interaction of two things. First, we have a crystal symmetry, and this crystal symmetry makes the crystals feeling external processes in certain directions in a different way. Now, you, for example, here in the case of our Gauss texture, the 100 direction feels a magnetic field in a different way than the 111 direction. If I would put a strong magnetic field on this sample, then it would probably try to orient such that the energy is minimized, if you allow the sample to do that, and probably all grains would start to turn versus 100, if they can. Yeah? If you allow them to be somehow flexible, rotating or something, they would probably start making a texture of 100 if you put them in a magnetic field. So, and this magnetic field is a process which I apply to that sample. So, and this process has a direction. For example, I say, I put a magnetic field in this direction, or I put a mechanical force in this direction, and the crystal symmetry will react with the process symmetry and creates a texture. So both comes together, sample symmetry or process symmetry and crystal symmetry, and they together make the texture. Okay, so it's the anisotropy of the crystals, crystal symmetry, together with the anisotropy of the process that creates the texture. And then the texture, of course, contains information of the process which has been creating it. And that is interesting because, particularly for geologists, by measuring the texture, they find out what happened to my rock. They don't know the process. We as engineers, we of course know our process. We know it has been rolled in this direction and it has been heated up to 1000 degrees. We should at least know that. No? If you are in the lab and your sample falls down and, oh, which was the direction, then you need to make a texture measurement to find it back. No? If you don't write it down. But it's important that you keep your sample properly oriented, no? At least if you deal with textures and crystal orientations. And the second thing is, of course, materials have anisotropic properties. No? A crystal pulled in one direction has a different strength than in the other direction. And if you have a texture, then also your bulk material has different anisotropic properties. And that's what interests us as engineers mostly. Can I have a homogeneous property? In all directions it deforms the same way. In all directions I have the same magnetic or optoelectronic properties. That's why we do all these measurements. So this is clear why we need texture. There's still a definition. So the orientation distribution function of a crystal or of a material, of a sample, that is a function which describes, so the texture itself just describes how many orientations, how many crystals have which orientation. But now we define a function, the orientation distribution function called ODF, which describes in a functional way how many orientations are at that place, and everywhere here inside. Yeah. So, and we have seen this texture here already, and good. Let's skip over that. It's not so important now. Why calculating the ODF? Why calculating this orientation distribution function? So, good. Let me go shortly back to this picture, which I wanted to show you here. I could simply plot 100,000 measurements into this plot here, and then display the people, okay, look, this is my texture. But I might, then you also need to keep in your memory 100,000 of measurements. And you must, and the people will not say, okay, how many points are overlapping here? Is this 100 or is this only 10? I don't see it, no? So you want to give people a value. How many pixels are overlapping here? How many crystals are belonging to that? How much volume percent is that? And you also want to reduce memory to memorize these textures. And therefore, you need these ODFs. So first you want to describe which orientations do I have, what's the distribution, how many of them are there, and how quickly do they fade away in space, in orientation space. Then you want to reduce data. Instead of 100,000 orientations, you just want to memorize one functional value. And then X-ray texture bears more problems. With EBSD, you measure orientations directly. Yeah? So in principle, you measure directly the orientation distribution. By every point gives an orientation. But when you do X-ray texture measurements, you're not measuring the orientations, you're just measuring the pole figures. You're just measuring this thing here, and you don't know which orientation belongs to it. Yeah? You just know the distribution of plane directions, but you don't know the distribution of orientations. So in X-ray texture measurement, you actually need to calculate the ODF from the pole figures to get the orientation to understand which kind of orientations are behind that. No? Good, but we're not doing that. EBSD is in this regard a much more straightforward and much more powerful technique. We're doing individual orientation measurements and not pole measurements. So, and now we're coming quickly now to the orientation measurements. And for that we must remember an orientation is a rotation. That means at latest after 360 degree, I'm back. Yeah, it's even valid for me. Yeah, if I turn myself 360 degree, then I look exactly the same again. No? I may smile and I may not smile before and after, but for the texture this is not the case. So we have a function which repeats after 360 degree at latest, and that's helpful to remember. At least 360. It could be even less. It could repeat already. For me, it's not true. When I turn only 180 degree, I look different, I believe. No? I haven't seen it yet. But I think it was. Okay. For textures, clearly it's a rotational function. And that means we can approximate a texture by a periodic function, by a function which repeats regularly after a rotation of 360 degree. And one function and one approach to that we all know, it's the cosinus and sinus functions. They repeat after 360 degree. Yeah? So you have, I clean up. Good, so you have a cosinus function, sinus function, which repeats at latest after 360 degree. Good, after 2 pi. But you could also say, okay, I take a sinus function with a higher frequency, which repeats already after 180 degree. Yeah? And or I could make a still higher frequency, and so on. And now imagine you have a function which consists, it's a kind of a measured function, yeah, which looks somehow like that. And then it repeats. Yeah, after 360 degree, it repeats. And now you say, okay, could I explain this function, because it repeats, by a set of sinus and cosinuses? Yes, I can. Actually, I'm able to select, okay, let's take 2 of this, plus 1 of this, plus 3 of this, and add them all together, and then I will approximate this function approximately. Oh, say, that's not bad, no badly drawn, but in principle, every periodic function you can approximate by a series of sinus and cosinuses, and that is the basics of the Fourier transform or of the Fourier series expansion analysis. You need it for electron microscopy, you need it for sound analysis, you need it for texture analysis. Fourier transform is something very important, and I would almost like to show you my music, but I will do that another time. We can plot sinus and cosinuses in form of music, and then you can start making sounds, not really music, but making sounds of any kind of function. And that's quite interesting. But having given you this, now this is a one-dimensional function. You have only one x coordinate system over which you change your function. But texture is, of course, a three-dimensional function. It repeats in three directions. Phi 1, phi 2 in Euler space, or in Rodriguez space R1, R2, or Rx, Ry, Rz. So we need a function which is a bit more complex than just this simple summation of sinuses and cosinuses. Ah yeah, there is mentioned I even show a picture, I think. Here is the mathematical background of exactly what I explained to you here. You can describe every kind of function, every kind of periodic function by a set of cosinuses and sinuses. And here is even the rule how you get the weight functions. So I have a weight ak and a weight bk for the different functions, and then you calculate these weight factors here, and then you get an explanation. And for example, here it's not perfectly seen. This is from Wikipedia. In principle, you have a rectangular function, and you're now calculating how much of these individual functions do you need to approach a rectangular function. And you see here is a cosinus, and then there's a cosinus with subcosinuses, or a sinus, and then you finally explain better and better this rectangular function. Okay. Now in textures you do exactly the same, just you don't use the simple sinus and cosinus functions, but you use functions which look a little bit more ugly. But in principle, it's exactly that. And more you don't really need to know. The rest is incorporated into software. If you want to write software for texture analysis, then I would say stop wasting your time. Yeah? Because for 30 years ago, people have spent so much time, it's all done, it's all understood. There's no new things, and it's really a very lengthy programming. So what we are using instead of sinuses and cosinuses is a series of generalized spherical harmonics. But this is in principle three-dimensional cosinuses and sinuses. Nothing special. And they look a little bit, and three-dimensional means we have a summation in 3 dimensions. Yeah? That's why we have it here. And this is the weight function. It's the weight factor, and this is the spherical harmonics. I think it's written here even, that is the spherical harmonics, so this is sinus or cosinus, and this one is, oops, there should be coming more. Oh yeah, okay, now it becomes funny. So this spherical harmonics is a function of phi 1, phi 2, or of the orientation if you want, yeah, and it should be written somewhere here. So it's an exponent. It's an imaginary exponential multiplied with this p of cosinus or whatever. It's a relatively ugly-looking function, and this p is even looking more ugly. It's a Legendre polynomial, and you would have to look into this. I mean, it's also not rocket mathematics again. It's just a summation over some factors. Yeah. And if you carefully write down, then you come to this Legendre polynomial, and so the equation continues here. And at the end, you have a very lengthy formula, which is just this one here. And now, here I said we go to 1 times this, 2 times this, 3 times this. We have 3 terms, 3 sinus and cosinus terms to describe some function. And how many terms you add, how many sinus and cosinuses or how many generalized spherical harmonics. This is described by the rank or by the series expansion degree. If L is 22, that means you will expand your series up to 22 different sorts of functions. Yeah? And they become finer and finer. First you have a very coarse behavior, then a finer behavior, then a finer behavior, and still finer, and you add them all together to describe your experimental function. And then the C coefficients, you may have heard about that, they give the weight. They say I need 50% of T1, 20% of T2, 30% of T3, and so on. And then you need of course to say, okay, what means 100%, yeah, or what means 1? So I need a normalization condition, and this normalization condition means if I calculate the integral over the whole orientation space, then I want to have an integral intensity of 1. I want to call this 1. This is my definition. And that means, and I will call this random distribution. So I take all grains and distribute them completely random. I put them in a box, shake well, put them on the table, and this I call the random distribution, and this should have the orientation density 1. Okay, and that is my normalization condition. This is just to let you know how do we measure orientation. You don't have to write this software. No? MTEX is doing it, OIM is doing it, the different X-ray texture calculation programs are doing it. Don't do it yourself. No? Oh yeah, and then important, this will, when you start writing it yourself, then you will get in trouble when you start. The general spherical harmonics, generalized spherical harmonics are still something relatively simple to understand. But then you have also crystal and sample symmetry. And you need to start to involve the crystal and sample symmetry in these calculations. And then these calculations, somehow they modify in here. I don't know exactly how, but you need to indicate, and that is not shown in this case, but in the case later, you indicate here with some dots on there, usually, which kind of T function you mean. Do you mean one for crystals, for cubic crystal symmetry, for hexagonal crystal symmetry, for orthotropic sample symmetry, and so on. Every time you have a different set of polynomials. And yes, now knowing this, I can show you how they look like. Yeah? And this is actually not only the functions look funnily bent, but also my Euler space is a little funny bent because I simply copied it out of the famous book of Bunge. In an old-fashioned way, I took really copies out of the book because I didn't find it electronically, and that's why my copies are a little bit distorted. But everything is distorted in Euler space, so it doesn't matter whether the coordinate system is also, yeah. So this is, for example, this is the spherical harmonics for the function T124. This means how far I expanded, how many sinus and cosinuses I add for orthotropic, for cubic sample symmetry and orthorhombic, cubic crystal symmetry and orthorhombic sample symmetry. And this is the T144, so higher development. It's already quicker. This is still quicker, T126 and T146. And you see these things become finer and finer. And in principle, you just you take out of this box here, I take a bit of this one, I add it. I take a bit of this one, I add it, until I explain the distribution of densities of my experiment. And that's what we are doing when we do texture calculation. So when we do the determination of C coefficients. And now I need to look again what is written here actually. Yeah, right. The basic principle is now, or the basic idea is now, and when you do texture analysis or when a software does it for you, is to find out what is the weight factor of all these individual contributions. Yeah? So once again, how much volume percent of this do I need, how much of that, how much of that, and of that. And there is, again, mathematics involved behind to calculate these. And this is, if you have X-ray texture measurements, then you don't have orientations. Yeah? You have just projections of orientations called pole figures. And then you need to calculate the C coefficients out of this projection. And that means out of the inversion of the orientation distribution function. And that is quite a complicated process. When we are dealing with individual measured orientations, then it's much simpler. For every orientation which you measure with EBSD, you can define, actually, you can directly calculate what is its personal weight factor. And then you have many different orientations and you just add them together, you smooth them out, and you get actually relatively quickly an orientation distribution. And I don't go into details here. This is the mathematics behind, but once again, software is doing it for you. But now let me show you an example. And important is not, so this I forgot to mention, right? Is it here? That should be somewhere here, but I don't know where it is. Yeah, I mentioned this is for an individual orientation. One orientation you can calculate what is the C coefficient directly. It's this analytical solution. And now if you have 100 orientation solutions, then you just add them together to calculate all these C coefficients, but you must smooth them out. You must say, okay, if I put them together, how do I mix them together? How do I mix individual orientations? Each one is, in principle, an individual peak in orientation space. So how do I mix them together? And I do this normally by mixing this with a Gaussian smoothing function over it. And this Gaussian smoothing function, you can select how wide should it be. So let me plot that shortly again here. So imagine the orientation would be just a one-dimensional feature. So here's the orientation, G, yeah? And here is the intensity of this orientation, I. So that means how many orientations we have. If we have just one orientation, one single one, we have just one peak here. So it's in principle infinitively high and infinitively sharp. So now I have, however, I have measured one orientation, 2, 3, 4, and so I have measured many of these orientations. And how do I get the average of it? I smooth it with a Gaussian smoothing. Yeah? And this Gaussian width, so actually I give every one of these orientations a Gaussian smoothing, and then I get a general, you can't read it with a red one here. So every of these orientation gets a little Gaussian, and then I add them together and I get one Gaussian function. And that's actually what you have to indicate to the software. You say, I smooth every of these individual orientations by 5 degrees. That may sometimes, if your texture is sharper than 5 degrees, you will add an additional softening to your texture. No? Then suddenly your texture will be at least 5 degrees if you select 5 degrees as a Gaussian smoothing. So you would go for a smaller value, but usually this is a good default value. And then you add them all together and you let them calculate the ODFs, these funny spherical harmonics, up to a rank of 16 or a rank of 32 and so on. And you can imagine the longer I calculate, first the more numbers I get, and the longer it's the calculation. The calculations become quite lengthy. If you go up to a development degree of 40 or so, it calculates hours. Yeah? If you go to 16, it calculates 60 seconds. So you remember perhaps the orientation distribution of the iron silicon steel, which I showed you before, and all these individual dots, which we saw several times. And now I have taken that and calculated the ODF of it. And now we're no longer plotting individual spots, but instead of that, we are plotting the density of these spots in principle. No? And that's what is now shown here. And overlaying here is the spots which came in, which gave the original orientation. And here you see something interesting, actually. You see there's many spots. Here's one peak, and here's the similar peak. But there is many spots, and there is few spots. Yeah? And the reason for that is that I have limited with my plotting with the plotting only up to 90 degrees. So I'm missing some of the symmetrically equivalent points. Yeah? That's why we are seeing a little bit difference in the spot densities, although in principle it's all there. I would have to plot all the way to 180 degrees to see the full density and correct correspondence of spots. But you see how it fits together. And now, so this was measured up to an expansion rank of 16, and we get then a maximum intensity of 6. That means the maximum, which is probably here, is there are 6 times more points than if I would distribute all these points randomly in space. If I would cover it all randomly with black dots, I have 6 times more than in this case. That means this intensity here. But now let's calculate the same thing. And then, okay, little point. Once we have calculated this ODF, the orientation distribution function, then of course I can calculate from that everything else. I can calculate pole figures, every kind of orientation distributions. For example, here, normal pole figures, inverse pole figures, as we spoke about. I can also calculate the Rodriguez space or the Euler space or whatever you want from it. Let's not go into details there. But now let's see how the expansion rank here influences the texture. So this was now calculated only with few expansions, with few sets of textures. And you see it looks much coarser than it looked before. So we have only a very smooth changing of the textures. And this one here is calculated with L equal 22. We have much sharper behavior. We have smaller variations available with LN22. That means these peaks here are sharper. And you will see that also when we go to L equal 8, maximum intensity is 3. We are smoothing out all these little dips and valleys. While if we go to L equal 22, we see 6 or almost 7. Yeah? So the texture is double as sharp than in this case. This calculates in less than a second, and this calculates already, I don't know, 10 seconds. And also, okay, this is written here, we need only 40 C coefficients here, and we need already almost 700 C coefficients there. And I have actually, I could show you this, oh yeah, maybe for fun, I show you shortly this files. If I click here, does it open it? No. I shortly have to look whether I find it. Where is it? Probably here. Oh yeah, here. I think. Yes, this is all the C coefficients, only 40 for the different for the different spherical harmonics. Yeah, the weights. And so you see here actually at the end is and you always have a real and an imaginary part of the C coefficients, and you see these weights here. No? And if you go for the 22, this list is already significantly longer. And of course, it's now the question, do I need all these 700 information? Or is L equal 8, is that already sufficient to describe the major details? Or do I need to go to higher development degrees? Also important is, which one is the right sharpness? Is it 7 or is it 3? Is the texture sharpness. So you have to actually, you need to get a little bit of experience, and you need to compare your measured texture with the calculated texture to make sure, okay, I see all the major features. Yeah? Or when I go to a higher expansion rank, it does not become better. Then you can say, okay, I can stop at 16 or at 8 or something like that. So, and of course, very important is you must make sure that you have sufficient input data. If you measure only 2 points, then it's not reasonable to calculate a texture which contains 400 descriptions. Yeah? So, but you must make, there's a rule of thumb, and I can recommend you to read one of our papers as well. A rule of thumb was that you need about 1,000 orientation measurements, well distributed over your sample, to have a reasonable idea of texture. We measured ourselves on DP steels in this case, and we found you get really an approximation to the real texture only after 10 to 50,000 measurements. Yeah, so it's a little bit, you need to test that, how many orientations you need to measure and how high you have to develop them before you get a proper and true description of your texture. I can even not give you really now a number, because if you have a very sharp texture, it's sufficient to measure just 10 grains and you are sure that you have it. If you have a very soft texture, you may measure 10,000 grains and it's still not enough to describe. No? So you need to try with the software, when do I see that the texture doesn't evolve any longer? No? Or, for example, if you have a sample and you have measured with eBSD just a little corner, and you get a nice texture out of it. Now go into another corner and measure again and see, is this texture identical? And if it's not, then you remember, okay, obviously I need to measure a larger area, or I need to measure at 4 different corners and add that together. So this is, maybe not all of you are interested in getting a proper texture, but if you need that, then this is quite an important consideration. How do I sample, my specimen, in order to get proper data? And what we do, and that was what I explained earlier this morning, we have developed software which, if you want to measure a very accurate texture, you make lots of little maps distributed over a maybe several centimeter large area, several centimeters, and you make lots of small maps, regular distributed, and you add them all together. Then you can be quite sure that your texture is right. Yeah? And we see then it becomes much more accurate and much more informative than any kind of X-ray measured texture. Okay, I think I'm close to ready. Yes, I am. I think that was it. Yes. Yeah, I think I can stop at that moment. There would be more details, but I think at that moment it's good to make an interruption, and I think you have obtained the major ideas about texture analysis. There's also other ways to do it, but for this time I come back next year. Huh? I threaten you already with this one right now, no? And then we can talk about more details. And this afternoon, or even after the break, we'll start making some examples. I plug in the OIM software and I will show you some funny things about texture and microstructure analysis with this. All right? Good, thank you very much. Yeah. Mm-hmm.